Okay, so on the last class we reached up to here. Okay, so the elitism versus diversity in the genetic algorithm. Okay, so next is some crossover methods for floating point genetic algorithm. That is, suppose you have two parents x1 and x2. How to do the crossover or mating between them? So we already studied this arithmetic crossover or linear interpolation between the two parents. So the two parents are x1 and x2. You have to select a random number beta between 0 and 1. So offspring 1 is beta into x1 plus 1 minus beta into x2. Offspring 2 is 1 minus beta into x1 plus beta into x2. So this will only give two offsprings inside the range of the two parents. Okay, suppose x1 is here, x2 is here, and beta equal to say zero point 0.3. Okay, so x1 apostrophe, the first offspring will be at a distance of 30% from x1, and second offspring will be, that is x2 apostrophe, will be a distance of 30% from x2. So, but actually we also need to extrapolate. Okay, we also need to explore the the regions outside x1 and x2. Okay, so arithmetic crossover will not explore the regions outside the range of x1 and x2. So for that there is another crossover called heuristic crossover, which will do both extrapolation and interpolation. And this is the most popular type of crossover used in the floating point genetic algorithm. So the method is like this. Offspring 1 is defined as beta into x1 minus x2 plus x1. Offspring proof is 2 is x2 plus beta into x2 minus x1. So beta is a positive random number between 0 and 1. These two offsprings will be extrapolated. So they will be out of the range of x1 and x2. Some example is given here. Suppose x1 equal to 2, x2 equal to 10, and beta equal to 0.2. Then offsprings are 0.4 and 11.6. So that is out of the range of x1 and x2. So two offsprings are obtained like this. Okay. Then beta is a negative random number between 0 and minus 1. It will interpolate. So you get two offsprings interpolated. So the method is that you have to both obtain both interpolated and extrapolated offsprings. That is four numbers. And randomly pick two out of them. So first you have to give a beta which is a positive random number between 0 and 1. Then again you have to generate another beta which is a negative random number between 0 and 1, 0 and minus 1, and you get four offsprings and you choose two out of them. So this is called heuristic crossover, which will do both extrapolation and interpolation. And there's another type of crossover called linear crossover, which is seldom used. Okay, this is some old type of method. Here three offsprings are produced, out of which the best two or at least two at random are taken. So the method is offspring 1 is 0.5 into x1 plus 0.5 into x2. This is actually mean of x1 and x2. Offspring 2 is 1.5 into x1 minus 1.5 into x2. That is extrapolation, and offspring 3 is this. Okay, so suppose this is x1 and x2. So one offspring is here at 50% of the distance from x1 and x2. Another offspring will be 50% outside x2, and another offspring will be 50% outside x1. So offspring, so this three offsprings are there, out of which you have to pick two. So some example is given here like this. Okay. Then mutation in binary genetic algorithm versus mutation in continuous genetic algorithm. What is the difference in specifying these things? So mutation in binary genetic algorithm is carried out in bits. So the probability of mutating a bit has to be specified. So if you refer to our first worked example where we tried the binary genetic algorithm on a single variable objective function, so 22 bits per member are there and total of 10 members are there. Okay, so X1 is, okay, 22 bits, okay, like this. And X2 is 22 bits like this. This is our first genetic algorithm example, okay. Similarly, X10 is 22 bits like this, okay. So 22 bits, 22 bits, 22 bits. So 220 bits are there in the population. So you have to specify how many bits you want to mutate. See, I want to mutate 2 bits here, 2 randomly picked bits. So the probability of mutation is 2 by 220. So in some binary genetic algorithm, you have to specify the probability of mutation, 2 by 220. So how is it? Okay, so probability of mutation is 0.00909. So how do you practically do this mutation? Okay. So what it done is, it can be practically implemented by generating 2 random numbers between 1 and 220 and mutating the corresponding bits. Oh, okay, so first you generate a random number equal to 10. So you mutate the 10th bit, okay? 10th bit from the starting bit. This is the 10th bit. And next you generate R equal to 56. R equal to 56 means it will be, okay, so this is 22, 22, 44. Okay, so 56 may be somewhere here. 44 plus 22. Okay, so 56th bit may be somewhere in the third member. Okay, so that is how mutation in binary genetic algorithm is practically carried out. It's a bit difficult to do this. Then mutation probability for continuous genetic algorithm or real coded genetic algorithm is a large value because it is probability of mutating a member. It is not probability of mutating a bit. So if you want to mutate 5 members out of a population of 100, mutation probability is 5%. Okay. So this can be implemented by generating 5 random numbers between 1 and 100 and replacing those 5 members. Okay. So mutation in the genetic algorithm will appear like a small number, 0.00909, but it will have the same effect of mutating 2 members. So if we change a bit in X1, it is equivalent to removing X1 and creating a new number. And if you change a bit in X3, it is equivalent to removing X3 and replacing it with a new member. Okay. So that is achieved in the floating point genetic algorithm by simply removing 2 members. Okay. So this illustrates the complexity of the binary genetic algorithm. Okay, then uniform mutation and non-uniform mutation. Uniform mutation means here the mutation probability is constant in all generations. Non-uniform mutation means here the mutation probability is decreased linearly or non-linearly with generations. Okay. So therefore, the random search is reduced in later generations. The idea is that you have to reduce the mutation in later generations in order not to spoil the population. Because in the later generations, we are going towards the global optima. So the solutions are getting better and better. So too much mutations at this stage will spoil the population. So according to this logic, you should reduce the mutation as the iterations increase. So that is called non-uniform mutation. But all the genetic algorithm which is there in the MATLAB toolbox and all have uniform mutation. Okay, then selecting typical genetic algorithm parameters. First is population size. It will vary from 50 to 500. It depends on the difficulty of the objective function. Okay, the objective function has many peaks. Then you need to sample it at many points. Okay, then you need a large population to sample this entire space. Okay, but as you increase the population, computational effort increases. Then crossover rate. Typically, it is between 40 to 60% of the total population. Okay, then number of crossovers. So maximum number of crossovers is population by 2. So if the population is 100, we can have 50 crossover operations, which will leave 50 into 2 offspring. Okay, which will completely fill the next generation. And then mutation probability. So 0.01 to 0.001 for binary genetic algorithm and up to 10% for continuous genetic algorithm. So 10% for continuous genetic algorithm means 10% of the population is randomly removed and replaced with new members. Okay. Then GA for multivariable problems. So here the complexity increases because up to now we only considered like this X versus Fx. Okay, X versus Fx, and a lot of peaks are there, and we need to find the global peak. And suppose X and Y is there. X is there, Y is there, and F of xy is there. Okay, some function like this, F of xy. Okay, so let us see how binary genetic algorithm will do it. Okay, suppose we want to maximize F of xy. So X is varying from -3 to 12.1. Okay, so let me wipe some. X is varying from -3 to 12.1 X, and Y is varying from 4.1 to 5.8. The Y range is very less in this problem, but X range is very large. Okay, and we want a resolution of 10 raised to -4 for both X and Y. Okay, so both X and Y, the resolution is 10 raised to -4. Okay, so X-axis needs 15.1 into 10 raised to 4 integer units, or 15 lakh integer units. X-axis needs 15 lakh integer units because its range is more. Okay, 15 lakh, and Y-axis needs only like 1.7 into 10 raised to 4, or 17,000 integer units. Okay, because Y-axis is short, you need only 17,000 integer units. So you can see that when you deal with two variable problems, all type of problems will occur for the binary genetic algorithm. So we need 18 bits to represent 15 lakh integers on the x-axis. We need 15 bits to represent 17,000 integers on the y-axis. So it's becoming more complicated for binary genetic algorithm. So the population of x1, y1, x2, y2 members are made and ranked according to f of xy values. Oh, okay, so this is one population x1, y1. This is another population x2, y2, etc. Okay. Okay. So in each population member, that is x1, y1, x2, y2, etc., x1 and y1 bits are joined together to form a single string. Okay. So the population of 10 will have 10 such strings. So let us see one member, okay, x1, y1, x2, and another member x2, y2. how it will look like. Okay, so x1, y1. So x1 is equal to 1.052, 1.052 something. Y1 is equal to 5.755 something. So the 18 bits of x1 are stuck together with 15 bits of y1. So we get a single string for one x1 y1 member. The next population member is x2 is equal to 3.13 something and y2 is equal to 4.99 something. So these two bits are stuck together. X1, Y1 bits are stuck together to form a single bit string. Okay, so this is one parent. This is another parent. Okay, so how do you do the crossover of these parents? So you have to cut it at multiple points. If it cuts only X or if it cuts only Y, then it will not mix the other parents. Yes. Okay, so multi-point crossover is required. So it is, we have to generate two random numbers, R1 and R2. Okay, so one random number cuts here, another random number cuts here. And you can swap the in between parts. Okay. So the cut has to pass both through X and the cut has to pass both through Y. Okay. Suppose both the cuts pass through X. Okay, then when you swap, then the Y coordinate will not change. The Y coordinate is not cut. So that is one problem with binary genetic algorithm. If you have multiple variables like X, Y, you have to make sufficient number of cuts so that the cuts will occur in both X and Y coordinates. Okay. So the two random numbers R1, R2, that is at the minimum, two random numbers R1 and R2 are required, and it will cut the bit string at two parts. Hopefully it will cut both X and Y. Okay. If both the cuts fall in the X, then the Y coordinate will be left undisturbed. Okay. So you may have to actually cut at 4 or 5 places in the hope that the cut will pass through both X and Y. So these are the complications of binary genetic algorithm. But
Sir,
if you did,
sir, how have you finalized 18 bits and 15 bits?
no, that is the number of integers. I told you, you need 15 lakh divisions in the x-axis. So you need to have 18 bits. You need to have 17,000 bits in the y-axis. So you need to have minimum 15 bits. Okay.
So in the next slide, you have put 01000 corresponding to x1 equal to 1.05, right?
Yeah.
How was that binary representation generated?
Now that you need a separate computer code. I am not showing
So that binary representation corresponds to that x1 value, sir.
Yeah. It actually doesn't correspond to x1 value. It corresponds to number of divisions to reach that x1 value. You have to count it like this. Okay. Until you reach x1 equal to 1.01, you have to count number of integers. Okay. That integer is converted to bits. Okay. Suppose you need 10,000 integers. 10,000 integers to reach this x is equal to 1.052. Then that 10,000 is converted to 18 bits. I think this I explained in the previous slide. Okay. Anyway, this binary thing will not be asked for exam except for some theory questions like how do you do the crossover for binary and how do you do the crossover for continuous. Okay. Only that will be asked. Okay, so next we come to the real coded genetic algorithm. So here everything becomes very simple. Okay. So what you do is that the floating point accuracy is set to 10 raised to -4. in MATLAB using the EPS command. This EPS is equal to 10 raised to minus 4 in MATLAB means that is the decimal accuracy. Okay. So with this simple command, we can set the accuracy, floating point accuracy for the continuous genetic algorithm. Then the population of X1, Y1, X2, Y2 is created and ranked according to f of x. Now suppose I want to cross over X1, Y1 and X2, Y2. Okay, so X1, Y1 is equal to 5, 10. X2, Y2 is equal to 25, 35. I want to cross them over. So what it done is that X1 and X2 are crossed over separately. So 5 and 25 are crossed over first. So that is X coordinate. So that will give the X1 apostrophe is equal to say 10. X2 apostrophe is equal to 12. Okay. So X1, X2 are crossed over separately. Okay. Then with another value of beta, another value of the random number, this Y1 and Y2 are crossed over separately. So 10 and 35 are crossed over separately. So Y1 apostrophe is maybe 21, Y2 apostrophe is equal to say 30. Okay, so now you got the offspring, first offspring, and this is actually second offspring. Okay, so everything is extremely easy in the floating point genetic algorithm. So it is because of this that people stopped using the binary genetic algorithm and almost everybody started using this floating point genetic algorithm. So binary genetic algorithm, I am illustrating to you only to show you the improvements in the genetic algorithm after that. Okay, that's some applications of genetic algorithm. Some worked out examples are there. To solve the genetic algorithm problem, you have to give the accuracy or the floating point solution, variable bounds of X and Y, population size, number of mutations required or probability of mutation, crossover rate, that is percentage of the population which is shortlisted as parents, the number of crossovers, that is NPOP by 2, population by 2, and type of crossover, arithmetic or heuristic, and number of iterations to run the GA, say 500 iterations. It will stop after 500 iterations, and you expect it to convert within 500 iterations. So some MATLAB GA code was used in these examples. Actually, this is not the MATLAB toolbox, but another freeware the MATLAB code is used for this 2-3 simple examples. The MATLAB GA toolbox will see after this. Okay, the first is our example of the non-convex objective function with multiple peaks. Okay, maximize this objective function. So this GAOT, it actually does maximization, I think. Okay, it does only maximization. So if you have objective function like this, only genetic algorithm will work. Okay, or only simulated annealing will work. The calculus-based methods will not work for this because depending on the starting point you give, it will find the next peak. So if you want to search this entire region and find this global peak, only genetic algorithm can work. Okay, so for many engineering applications, the objective function will look like this. It will not have just one peak. Okay, so objective function is given, variable bounds is given, that is 0 to 10. Both X and Y are from 0 to 10. Then accuracy is The floating point accuracy is 10 raised to minus 8. Okay, so in the genetic algorithm code, you have to set the variable bounds of x and y as 0 and 10. Population size is taken as 100 because this is a complicated objective function. Then 40% of the population is shortlisted as parents. Remaining 60% are rejected. Number of crossovers is 50. Okay. So if you do 50 crossover, you will get population of 100, which will fill the next generation completely. So in the so you have to write the MATLAB code for this objective function, and that has to be linked with the genetic algorithm subroutine. Those things we'll see later. So set 100 iterations to termination. Okay. So you can see that after this 100 iterations, we get the correct solution. That is x, y is equal to 9.8 to 10. So you can see that. Okay, so f of xy equal to 20. You could, okay, so this is the correct answer. F of xy equal to 20. So it has identified the correct peak. Then x is equal to 9.82. So this distance is 9.82, and you can see a small gap here. Okay, like 0.18 or something. Okay, and y is equal to 10. Okay, so this is x, this is y. So y is equal to 10. This is y. Okay, so it has correctly found the peak. The another thing is that how do you check the convergence of the fitness function? Or how do you check convergence of this algorithm? So what you have to do is that you have to continuously monitor the maximum fitness of the population or the fitness of the best member of the population and the average fitness of all the members of the population. So what will happen is that finally all these members, all these populations will converge to the global peak. So this is the maximum fitness. Okay, and average fitness will be somewhere here. This is average fitness. This is maximum fitness. Okay, so the average fitness will approach the maximum fitness as the points come closer together. So you can see that it has almost reached close together. Okay, so that means another maybe 20 iterations may be needed before all the populations converge to the maximum. Okay, then this is also the same objective function. Minimize the objective function, but because the genetic algorithm will do only maximization, you have to maximize the negative of the objective function. So this is also the same thing. It has found the correct answer. Actually, this minima we can't see because it is under the bottom of the curves. We can see only the top of the curve, but this answer is right. Okay, so here also you can plot the maximum fitness or the fitness of the best member of the population and average fitness of all the members of the population. So you can see that it has come close. Okay. So this we can skip. So we look at this example. Okay. Eigenvalue control of a 3-degree of freedom system with genetic algorithm. So here you can see lumped mass spring system. The value of the lumped masses is 50 kilogram each, and the K1, K2 K3 is 50,000 Newton per meter spring stiffness. So this is the starting values which is given to you. Starting value. Starting values of M and K which is given to you, and this is the mass matrix, stiffness matrix, and this is how you find the eigenvalues. So our starting eigenvalues are like this. So if you use these values, you will get these eigenvalues. So first natural frequency is 14.7. Second natural frequency is 39.43. Third one is 56.98. So what is the question? Question is that you have to find K1, K2, K3 such that omega 1 is maintained exactly at 14.7. Omega 2 is changed to 35. That is originally to 39.43. We want to change it to 35. Omega 3 we are not bothered. That's the third natural frequency, and people are not that much bothered with the high values. Okay. So our goal is find values of K1 and K2 and K3 within this search range such that omega 1 is unchanged, omega 2 is becoming exactly 35 radians per second. Okay. So how this is done with genetic algorithm? So this is a 3 variable problem. So design variables are 3, K1, K2, K3, like X, Y, Z. Okay. X, Y, Z. So each of them have the same search range, that is 30,000 to 70,000. Then you have to write the objective function for maximization. So the objective function consists of two parts, part A and part B. So part A is designed to keep omega 1 at 14.7, and part B is designed to force omega 2 to become 35. Okay, so this is also called multi-objective optimization. So how is this done? So the objective function must reach a maximum value when omega 1 reaches 14.7 and simultaneously omega 2 reaches 35. So how do you write such an objective function? So such an objective function is written like this. So maximize the negative of absolute value of 14.7 minus omega 1 minus the absolute value of 35 minus omega 2. So this denominators are weighting values, okay, to maintain the same relative values. Okay, so actually the numerators are more important. So it can be seen that the maximum value of each term of the objective function is 0. So this minus of absolute of 14.7 minus omega 1 will reach a maximum value of 0 when omega 1 equals 14.7. And this minus of absolute value of 35 minus omega 2 will reach maximum value of 0 when omega 2 equals 35. So for all values of omega 2, this numerator will have a negative value. Okay. Okay, so now you have to write all the subroutines to calculate the eigenvalues and all that. And those subroutines are a part of the objective function subroutine of this genetic algorithm. So this GA program is run using the standard parameter, that is population equal to 100, then crossover equal to 40%, and then mutation equal to 10%, etc. Okay. 200. Okay. Mutation equal to 5%, etc. Okay. So what is happening is that each time you run the GA, we get a different solution, but all of it satisfy the objective function. So when the genetic algorithm is run first, you get this solution. K1 equal to 55,000, K2 equal to 69,000, K3 equal to 32,000. And omega 1 is coming exactly to 14.7. Omega 2 is coming to 34.98, okay, which is close to 35. Then when you run the genetic algorithm again, because the population is different, the starting population is different, you get another values of K1, K2, K3, which also gives almost the same results. That is, omega 1 is 14.7 and omega 2 is exactly 35. So this could be because there are many equal peaks in the objective function. Okay, so two equal peaks are there. Okay, so they give the same value of f of x1. So first time you run the genetic algorithm, everything will converge here. Next time you run the genetic algorithm, everything will converge here. But if one peak is bigger than the other, then this issue is not there. But in this particular problem, it seems that there are multiple peaks having almost the same objective function value. Then each run you will get different results. Okay. So many engineering problems are like this. So one method is to restrict the range of K1, K2, K3 within a narrower range. Then you will get only this peak. So in this case, we are given a wide range for K1, K2, K3, etc. So multiple peaks with equal height are occurring in that range. Okay. So here also we get this. We are only getting this maximum fitness here. Okay. Okay, we can stop here. Okay, we can stop here, and next class we'll start with the new topic, that is multi-objective optimization.
Okay, sir.
So the genetic algorithm we ask for NSUM and the next assignment. You have to show one, you will be given an initial population, and you have to show one sample iteration. That is how you get the next generation. Okay, you have to do one or two crossovers. You have to rank the population, eliminate 50% of the worst, etc. Okay.
Okay, sir.
Okay.
Assignment.
So let us take the attendance. Stop.
Exam.